So good afternoon, friends. Today we'll discuss the preparation and the standardization of sodium thiosulfate solution. This is also example Redox titration. The reference I have taken from the Beckett Stanley. So you can go through that book itself, Beckett Stanley practical book of pharmaceutical chemistry. And this titration is a type of a redox titration, and in here the we are going to estimate out the normality of sodium thiosulfate solution prepared. As we know, this sodium thiosulfate solution is acting as a secondary standard, so it need to be standardized. So it will be standardized with the help of a primary standard. So here the primary standard which we are going to take is a potassium dichromate. So with the help of potassium dichromate, we are going to standardize it. So the example of this redox titration, it is a type of a iodometric titration. And what is iodometric here is, iodometric is nothing but the indirect titration. That means indirect. Why it is termed indirect? Because here we won't take directly iodine. Here iodine is liberated with the help of certain chemical. So liberation of iodine depends on the reagent that we take. So here this iodine got liberated with the help of potassium iodide. So here this sodium thiosulfate is going to react with that iodine. So this iodine will come from the potassium iodide. So we will take the potassium dichromate as a primary standard here. So potassium dichromate, when you will say Cr2O7, 2 negative can be written. When it reacts with this Ki, that is iodide, here this potassium dichromate is acting as a oxidizing agent, and this iodide is acting as a reducing agent. In the presence of a acidic media, it will convert into chromium ion, and this chromium ion is found to have the green color, and it will convert into iodine. Iodine will having the brown color. So our flask will be brown in color due to the presence of this iodine, and there will be formation of water molecule. When you will balance it, it will be just like this 2I, and this is 14, this is 7. So it will be, and there will liberated iodine will be there. This liberated iodine will be titrated with the help of sodium thiosulfate, Na2S2O3. This is sodium thiosulfate. It will be titrated with iodine. So it will form the tetrathionate. That is the Na4 uh, Na2S4O6. That is the sodium tetrathionate, and it will form the NaI, that is the sodium iodide, that is the two molecule of sodium iodide, and there will be the two molecules of sodium thiosulfate is going to participate. So this is a theory behind that. This why it is some iodometry, because here iodine is liberated, and the liberated iodine is titrated with the help of sodium thiosulfate solution. Now when you will see the marketed sodium thiosulfate solution, you will find it is of having molecular weight 248.17. When it is available in anhydrous form, it is molecular weight is 148.11. So in order to prepare, if we have to prepare zero point 0.1 normal and 1 liter solution, so for that, if we are having 5H2O sodium thiosulfate, so we will take 24.8 gram directly sodium thiosulfate solution and make it to dissolve in 1 liter of distilled water. So we will get the zero point 0.1 normal sodium thiosulfate solution. If we are having the anhydrous, so we will take 15.8 gram of sodium thiosulfate and dissolve in 1 liter of distilled water. So this is a way by which the sodium thiosulfate solution will be prepared. Then potassium dichromate solution has to be prepared. So we know that titration has to be done in equinormal or equimolar solution. So here sodium thiosulfate we have taken is a zero point 0.1 normal. So automatically it has to be taken zero point 0.1 normal. So in order to prepare zero point 0.1 normal, and this is a primary standard. So we'll prepare 100 ml in 100 ml volumetric flask. So I am taking it as a zero point 0.1 100 ml. So here this potassium dichromate, the molecular weight of this is 294.187. So and this molecular weight of this equivalent weight of the sodium potassium chromate is nothing but potassium dichromate. It is potassium dichromate is nothing but divided by 6. So divided by 6 means 294 divided by 6. It will come around 49 something will come. That is 490.33. It will come out. So 490.33 is the equivalent weight for the 490 point, it is coming 490 gram, it is coming. uh, this is the equivalent weight. So 49.03 gram if you will take in 1 liter, so that will be zero point 0.1 normal. In order to prepare 100 ml, we will take 0.490 gram of that is accurately, it has to be weighed out with the help of chemical balance or the digital balance. Then it will be transferred into 100 ml volumetric flask, 100 ml volumetric flask, and with then it will be dissolved in distilled water. With the help of distilled water, it will be dissolved. So this will be the potassium dichromate solution. Then starch solution, 1% solution has to be prepared. So 1 gram of starch made to dissolve in 100 ml of distilled water, but it has to be dissolved with the help of heat. So it has to be taken into consideration that otherwise glutenization will not take place. That is responsible for the color. Otherwise, we won't get the color. And here potassium iodide will take 10% solution. So 10 gram of Ki will be made to dissolve in 100 ml of distilled water. 100 ml of distilled water उसमें हम dissolve कर लेंगे. Done. Now we'll take this reagent, sodium thiosulphate will take here in the urate, and in the then here the flask that we are going to take is the iodine flask that you must bear, because here the liberation of iodine is going to take place. Here we will take the potassium dichromate solution. So 20 ml of potassium dichromate solution, which we have prepared in the step number second. So that will take 20 ml. Then we'll add the 10 ml of that is a Ki solution, potassium iodide solution, which we have prepared, and we will add 10 ml of dilute H2SO4 we will add. Then uh, we will keep this iodine flask for the 5 minutes. We will keep it for 5 minutes. After left for 5 minutes. After 5 minutes is over, there will be the evolution of iodine is going to take place. Then the liberated iodine, which is liberating from this reaction of this potassium iodide and Ki and H2SO4, which we have seen in the previous in the above portion. So the liberated iodine will be now titrated with sodium thiosulfate. As the flask will be whole, flask will become brown due to the liberation of this iodine. So liberated iodine will be titrated with sodium thiosulfate. Slowly, this brown color got diminished. Brown color slowly diminish, and finally this color will going to disappear. But before disappearing the color, we will add the 1 ml of starch solution that is acting as a indicator. 1 ml starch solution will add, which is acting as an indicator here. So now the iodine which is left here is going to react with this starch, and the solution color will become blue. The solution will be of blue color now. Now afterward we will titrate again with the sodium thiosulfate until its color comes to green, because chromium ion is having the green color. So final color of the solution will become green. That time we will stop the titration and we will note the endpoint. Finally, we will repeat this titration with 20 ml of potassium dichromate solution, and we will note out the endpoint, whatever endpoint may come out. So here for the calculation part, I have kept the endpoint as 19.4. So we can suppose it is 19.4. Now, what part of calculations? First of all, we will write the weighing, whatever weighing of potassium dichromate we do. Suppose the weighing done is 0.049383 of potassium dichromate. Now what we'll do, we will calculate the normality of potassium dichromate with the help of this weighing. So we know weight upon equivalent weight into 1000 divided by volume of solution we have taken. So here weight is coming 0.4983, and equivalent weight you can say that is 49.03 of potassium dichromate. 1000 is same, and volume is 100 ml. Here we have prepared 100 ml solution. We will write 100 ml. So normality of potassium dichromate by the weighing it will come out. You can, when you will calculate, it will come out 1.1016. So this is the normality of potassium dichromate. This we have taken while taking one example so that it will be easy for us to solve the thing. Now we are having the normality of potassium dichromate with us. We have a volume of sodium thiosulfate and volume of potassium dichromate we have, that is a 20 ml. So by keeping this formula N1V1 is to N2V2, if we will keep it for potassium dichromate K2Cr2O7, and we will keep it for sodium thiosulfate Na2S2O3. So normality of potassium dichromate we have, we have calculated already. So N1 will be substituted with this 1.1016. Volume is 20. Potassium dichromate we have taken 20 ml, and sodium thiosulfate we have to calculate. So we will keep it N2. Volume of sodium thiosulfate is nothing but the endpoint. This will be the endpoint, that is a V2. This is V2, so we'll put the 19.4. So from this we can calculate the N2. So N2 will come, from this calculation it is coming like 1.047. So we can say the normality of sodium thiosulfate solution which we have prepared is having the normality of 10.1047. Thank you.